Looking at X-ray imaging. And this is an X-ray image of a human hand, okay? And it's a negative of the image in the sense that the bones are brighter, right? Which means that more photons were absorbed by the bones. Now, you could imagine, though, in the actual data when it was taken, you'd have a shadow cast by the bones, right? But when people look at it, they invert it historically. And so, is there any way to tell if that's the right or left hand? That's a problem you can take home and think about. But anyway, you can see this fantastic, spatial resolution. The detectors for, detecting X-rays in these systems are really high resolution now, and so are the X-ray production systems can basically produce X-rays from a point or something that's sort of a fraction of a millimeter, a couple of millimeters. The basic chain, X-ray chain, is here. We have X-ray light bulb shines X-rays through the patient, right? And then on the other side of the patient, we have a detector, and you detect the shadow cast by the patient. This is essentially a fluoroscopy system. Oftentimes, a physician will be doing an intervention while imaging. So they'll be putting in a stent into the person's aorta, or they'll be putting in a valve to their mitral valve, or they'll be injecting contrast agent to see vessels and things like that. So it's a very interactive system. The system itself can be turned on just by a foot pedal, and so the person's looking at a screen and they push their foot on the floor and then pictures come up, sort of at 15 frames a second or something like that. X-rays themselves are part of the electromagnetic spectrum. They're up here in terms of energy and wavelength. For us, the X-rays that we're interested in for diagnostic imaging currently fall between 70 and 140 keV. Somewhere in there is our zone. There are X-rays of lower energy that are impinging on the patient, but they rarely get through the patient. They don't make it to the detector, right? Because at lower and lower energies, the photoelectric absorption gets really high, as we'll see, and most of those X-rays are absorbed, right? They just go to dose. So you'd actually like to filter them away before you shine them onto the patient. This is a X-ray light bulb or a X-ray tube. So this is a vacuum. There's an anode and a cathode up here, and I'm gonna flip it over. I'm sorry about this. So now it's stuck to the ceiling because the diagram on the next page is in this orientation. So this is a motor, right? This is a metallic disc, or it's called an anode because it's positively charged in this system. And that metallic disc spins by using this motor. And the reason you spin the disc is because it's hard to see through here, but there's a cathode here. It's like a coil, filament coil that is heated up to a very high temperature, and X-rays come firing off this thing. Let me do laser. Come firing off this and hit the anode. Okay? And, sorry, not X-rays. Correct that. Electrons boil off this, are accelerated across here by a voltage and hit the anode. The electrons do. Okay? If this was stationary, you could do that for about 10 seconds, and then you just blow it. You burn a hole in the anode, right, with the current that we're talking about here. So what they do is they spin this anode around so that the target is continuously changing and being cooled. And cooling, it's being cooled through basically conduction this way. There's wires here that cause a very large voltage between this anode and this cathode, right? You can imagine we saw on the last page we're interested in 70 to 140 keV, right, is our photons that we're interested in. That's the energy of the photons we're interested in. So the electrons have to have that energy when they hit the target, at least, to produce photons that have this energy. And so we accelerate those electrons across this gap. It's in a vacuum. They hit the target, and the collision of those electrons with stuff in the target produces X-rays. Okay. Here's the basic diagram of that system. Cathode here, spinning anode in the vacuum. We're going to put current through the cathode at given milliamp, and we're going to set that anywhere from 50 to 1500 milliamps is where X-ray tubes operate now. The tungsten filament is heated up to a very high temperature to boil off these electrons. They accelerate across here, hit the target, and the X-rays come shooting out here. They go in all directions, but we'll collimate them to shoot out in one direction. Any questions about that? This thing's worth about $25,000 or something. It's a pretty expensive light bulb, 25 to 100 probably. And one of the big jumps in CT technology is making this thing powerful enough to image very fast, because you need a lot of X-rays in a short period of time, right? And so essentially you have to be able to put a lot of tube current in this thing and make a lot of X-rays with this thing in a short period of time. Okay? And so these tubes have gone up and up and up in performance over the last 3 decades. So it's like an X-ray light bulb. If you burn it out, it's a big deal. It costs a lot of money. So you don't want to do anything silly. You know, if you basically just image too much on a phantom or something like that, you can cause damage. And so usually there's things in the system that will stop you doing that. And heaven forbid you're doing it when there's a person being imaged, right? So there should be safeties in the system that don't let you put too many X-rays into a person. So how are the X-rays produced in that target? So now we're going to look and see what happens when a single electron comes here and hits the target. Okay. What happens to that electron is it comes through, 90% of them just basically hit other electrons in the tungsten and knock them in, and you get another electron flying through the tungsten at somewhat lower velocity, and then it hits another electron, goes through and hits another electron, and just by around this cascade of stuff happens, and the thing heats up. That's 90% of what happens. Okay? That doesn't produce any photons. It just produces heat in the target. That's too bad. Two primary ways of producing photons. One is that this electron coming from our cathode hits an inner shell electron in the target. That electron is ejected, and then an outer shell electron drops into the orbit of the K electron that you ejected from your target. And when this drops, the difference in energy between those two energy levels is emitted as a photon, right? And so it's just a quantum mechanical thing. It comes out at exactly the energy difference between this shell and this shell, that electron. And that's called a characteristic X-ray. It comes out at very specific energy, right? And it's a very sharp line on a spectrum. So this is how when, say, astronomers look at a star and they say, what's in the star? They look for these characteristic X-ray things from specific atoms. And that will tell you what's there. But principally, the X-rays we're going to use come from this source, which is called Bremsstrahlung. And Bremsstrahlung is German for breaking, apparently. And so what happens is the electron comes through, interacts with the atom by getting accelerated, from an electrostatic effect, sort of a charge effect. It comes through, gets really close to the nucleus, and it takes a hard turn, and then it loses energy in that process, and the energy comes out as a photon. Okay? And so a Bremsstrahlung photon is released, and these are released at energies anywhere from the maximum possible energy. So if this electron here's my nucleus, and it comes up and it does like a 180 or just like right into it, then you get the maximum release because you've got, say, 140 keV electron gets completely stopped, then 140 keV photon comes out. If it takes a hard break, a lower energy comes out. So we get a spectrum of photons coming out with this process. And this is what the spectrum looks like. If let's say we set our peak voltage on our tube to 120 keV, so I'm accelerating electrons across that gap between the cathode and the anode, and it's 120 keV voltage there. Then I can get photons, the relative intensity or number of photons, this is like a histogram, at different energies, just by the Bremsstrahlung process, looks like this. And it would continue, if none of these photons were filtered, it would continue up in a straight line to here. And that's the density or the intensity of the photons as a function of energy that come out of the tube. Here are the characteristic lines for a tungsten target. You know, these are the K-shell ejections. And then the relative X-ray intensity as we get to lower and lower energies drops. And the reason for that at those lower energies is those X-rays are absorbed, right, before they get to the patient. Or even actually, if you have your X-ray tube here, usually there's some kind of metallic filter right in front of the exit, and it takes out a lot of these low energy photons. And the glass in the tube, the tungsten target itself will absorb low energy X-rays that are trying to get out of the target. So you just don't see them when you look at what's coming out of your X-ray tube. And that's a good thing because all of these would never make it through the patient. So there's zero probability that one of those X-rays, when it enters the patient, is going to come out the back. All they would do is deposit energy in the patient. Right? And so you don't really want those photons going in there because they're not improving your image. They're just delivering dose to the patient. So if we then take our X-ray tube or our system and we turn the dial down to 100 keV peak, we get this spectrum of X-rays coming out of the system, and we image with that spectrum. So you can change the spectrum on your system. So what happens to the X-ray when it, travels through the patient or travels through anything? Okay. There's two dominant interactions of the X-ray with matter that we're concerned with in making contrast in X-ray pictures. The first is the photoelectric effect, and you can think of this as the incident photon sort of interacting chemically with the material itself. So where are we now? We've created a photon, it's coming out of our X-ray tube, it's going into a patient, and it's now going to interact with molecules in fat, bone, liver, blood, contrast agent, stuff like that. So that X-ray is coming through. If the X-ray goes all the way through the patient, we get a detected event on the other side, right? And if they all went through the patient, you wouldn't have a picture, right? All you'd see is just a bunch of X-rays there. There'd be no contrast. But they don't all go through. What you image is the shadow. It's like the difference, right? It's like the differential absorption as a function of position through the patient. So ideally, how many do you think you should have absorbed in the patient versus detected? Like, should 99% hit the detector, or should 1% hit the detector, or what? Anybody have a guess? If you just had to guess, or someone is going to take your lunch, I mean, you got to do an answer. Like, what's the answer? Nobody's going to guess. Huh?
I didn't bring one.
Yeah. You gotta commit. Everybody's going, yeah, I'm gonna do 50%.
I don't know.
It's like, I would have said 50%. That would be my guess, right? I have no idea what the answer is, so we can figure this out. Like, you basically have to have a bunch of photons detected to get any signal, right? If 99% are absorbed, you get only a few things, and your signal is going to be really poor. If 99% of the photons get through, you're going to have really good signal. You can measure the counts with high accuracy. Not much contrast, because you only got 1% of the photons didn't get through to cast the shadow. So it's sort of like, what is the shadow and what is the detected stuff? So it's an interesting question. Maybe we'll put it on a problem set. Okay, I don't know what the answer is. So two processes occur in the patient. One is photoelectric effect, where you can have the photon hit an electron in the atom. You get this photoelectron injected with a drop. Again, it's the same thing that we saw with the electron hitting the target, a drop of an outer shell back into a lower shell, and you get this characteristic radiation coming out. We're not going to use this radiation usually. This is just a way that the photons are getting absorbed. Remember, that's all we're talking about here. All we care about is that the photon gets absorbed. Right? And then, now I've forgotten how an Auger electron comes out. How does that happen? Does anyone know? How does an Auger electron come out? Well, I'll get back to this. It might come to me that I've forgotten. So anyway, this is the photoelectric effect, which is the interaction of the incident X-ray with sort of the chemical composition / electron shells of the material. And then the primary method for generating contrast or stopping these photons is Compton scattering. So what happens is we get a photon comes in, knocks an electron out of the atom, right? And then you get it doesn't give all of its energy off to that electron, but it scatters off at an angle. And then that photon, the scattered photon, can do that again. Right? And so you get a cascade of these Compton interactions such that the incident photon you had goes tut, 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 and then it's done. You don't detect it, and it's been absorbed. Right? If this angle is high enough as well, it might, say you don't have one Compton interaction, the photon came through, hit an electron, that electron goes off, the photon goes this way, it might miss your detector, right? Because it's high enough angle. So that's good. It got absorbed. Right? And so you're generating contrast. But it also, if the angle isn't high enough, right, it'll come through, deflect, and then hit the detector, but not on the correct line. It's hitting it from a different angle, right, which is quite confusing. That's called scatter. And so the energy dependence of these two effects are the following, in that the probability of having a photoelectric interaction goes basically as the atomic number to the fourth power and energy over energy cubed. Okay, so the energy of the photon itself. So the lower energy photons are much higher probability to interact with the electron shell and cause photoelectric effect. The higher energy photons are much less probable. For the Compton scattering, the probability goes as the atomic number, right, of the atom itself. So basically, the density of the electron cloud. We can see over the set of energies that we might see out of our X-ray tube, say 10 keV all the way out to 150. The percentage of interactions at that energy, which are Compton interactions. And you can see as we get up to about 50, 60, pretty well in this range, they're all essentially Compton interactions, right? By this time, the photoelectric stuff is not making a difference. And so here's a graph of that dependence. This is the photoelectric attenuation. So this is called the mass attenuation coefficient. So this is like proportional to how many photons you're going to absorb. And so going in this direction means you're absorbing more photons. This is energy. This is 200 keV right here. And as we go down in energy to, say, 20 keV across this dynamic range, the photoelectric effect gets higher and higher and higher and higher. So that down here in this energy, pretty well, photoelectric effect is the dominant mechanism. But then when we get out to about here, the Compton scattering is the dominant mechanism. And Compton scattering over our energy range, which is about here, right, is essentially constant as a function of energy. So we've got a spectrum of X-rays. They have essentially the same probability of undergoing Compton scattering across the energy that we're going to use for imaging. So that's inside this box. Our Compton scattering is pretty well constant, and the photoelectric effect varies considerably. Right? This gives us an opportunity, actually, to do multi-energy imaging. So if we take a X-ray picture, suppose we had a mono-energetic X-ray source, we could take a picture here at, say, this is 20, 30, 40 keV, 50 keV here, and we get this much, the ratio of photoelectric to Compton would be this, and then we take a 200 keV picture and there's no photoelectric effect, it's just all Compton. So those two pictures would look quite different. Right? So now you've got multi-dimensional data for different tissues. Right? That's called multispectral imaging. We might take a look at that. So the X-ray imaging chain, just to review, we have our X-ray light bulb here. We're going to put this filter here. It's usually copper or aluminum, just a little thin, constant piece of copper aluminum to take the low energy photons out of the beam so they don't just hit the patient and not get through. So that's that filter. We collimate this beam such that it illuminates an area of the patient that is minimum for what we want to see through that part of the patient. And then there's some kind of detector on the backside for the shadow. So in quantifying how the intensity of the X-rays change as a function of distance through the patient, we'll introduce some pretty simple math here. So, and this is all in Princeton links, so I would recommend reading chapter 4 to get the details of this and an alternative explanation. So the intensity is defined as the energy times the photon fluence, where photon fluence is the number of photons per unit area in a given time. Okay, so that's a fairly simple, sort of sensible definition of what photon fluence is and what intensity is. Intensity goes as energy because usually on the detector, if a higher energy thing, a higher energy photon hits the detector, you get a brighter, a bigger intensity signal than if it's a lower energy one. So it's linear with energy. The fluence, we already know what this looks like because we saw that diagram, the histogram. Here, this is the relative amount of X-rays at a specific energy. So if I look at this spectrum here, when I turn my voltage of my X-ray tube to 120, this is the relative number of photons as a function of energy that I get. So that is phi, right? When I integrate everything under here, that I get phi. So here's SE is this function here, and DE is, this axis here. So another interesting thing is as I crank the KVP down, I will get the phi value will drop because the integral under this curve goes down, so the total fluence of photons goes down as I'm dropping the voltage, the peak voltage. Right? And so the intensity, we just multiply by the energy, and that gives us the intensity. So I multiply each delta E here by its energy and its relative height, and that gives me the intensity. So how do you mathematically characterize how the X-rays get attenuated? We saw all the photoelectric effect and Compton are the mechanisms, the underlying machinery by which those photons are absorbed. But in just characterizing how many photons are emitted at the back end of the object after you put a beam through it, we use a very simple mathematical description, which is going to be quantified by a thing called the linear attenuation coefficient. And this gives you a sort of an overview of how this works. If I have, say, 1,000 photons hitting this object and 20% get absorbed by this thickness of this stuff, let's say this is, copper or something like that. 1,000 photons hit it, 20% get absorbed in there, so now I have 800 on this side, right? When 800 hit exactly a replicate of this here, what happens is I get 20% of those get absorbed. So you get 640, and again, 20% of those get absorbed, you get 512. When you plot that out, you get a very nice mono-exponential curve, right, that goes as distance accumulated through here, and this coefficient describing this exponential decay is called mu, and it's the linear attenuation coefficient. And that is dependent on what this substance is. Right? So if it's water, you will get a certain fraction of the X-rays will be absorbed. If it's water mixed with a contrast agent that has a lot of iodine, you get a lot more X-ray attenuation, so fewer come out, and this curve will go down much more quickly, right? And the mu value will be higher, right? So it's the linear attenuation coefficient. A very simple, nice way to describe it. There's a description in the book. I'm not going to dwell on it right now. You can go and derive this in as many ways as you want. It's a simple first-order differential equation which has a mono-exponential decay as its solution, right? So we have the number emerging, or the number that hit the target, multiplied by the width of the target times the linear attenuation coefficient. This is a interesting number to know for different materials because linear attenuation coefficients are given in inverse centimeters, and so it's like number of E decays per centimeter, and so people don't think in that unit or that system, and so you can ask the question, well, what value of delta X do I need of this material to get 50% of the photons absorbed? That's called the half value layer. And so, it's a very simple formula for HVL given if you know mu, but it gives you a visceral feeling for like, how much liver do I need to absorb 50% of the photons? Like, do I need 3 centimeters? Do I need 30 centimeters, right? And so some of your problems will look at that, and you'll get a feeling for how many photons get absorbed for a specific thickness of a material. Okay. So here's some, it's going to be energy dependent again. And so for muscle and bone, if this 100 keV, 50 to 100 is sort of where we're operating in clinical imaging. And you see it's like 3 to 4 centimeters, 50% of those photons will be gone. Okay. In bone, it's only 1 to 2 centimeters. This is an interesting aside. I think this is out of the book, out of Prints and Links, in that going back to our local contrast definition, where it's the fractional change in the signal compared to the background, when you do that, under the assumption that your signal coming through here is given by this equation, which is the amount of attenuation, so the relative amount of attenuation of X-rays, and you calculate the local contrast as that fraction, you get a very simple formula for what that contrast is. And so that's why it makes sense in X-ray imaging, projection X-ray imaging, to define contrast that way, because this comes out as a very simple thing. It's just, dependent on the thickness. However, when we go to determine, are we able to detect this bump here with respect to the background, I think we're going to measure A and B divided by the RMS of, we'll measure the contrast to noise. Okay, if we have a human, and they're about that thick, if we go through the chest this way and out their back that way, so they're about that thick, right? So we saw that a half value layer was 3 centimeters through a liver, so there's actually a fairly substantial amount of attenuation that's going to occur as we're passing through that person. But if I have my spot where my X-rays are coming from, and I draw a line from that spot to a detector element on my detector, so along that line, and ask, well, how many photons along that line are going to get absorbed? As I pass through the patient on that ray or that line, I'm passing through multiple different tissue types, right? I'll hit skin, then fat, then perhaps a rib, and then some muscle, and then lung, air, and then, the back of the rib, and then out, right? And so I've gone through some very heterogeneous X-ray attenuation as I move through that tissue. And so to characterize that mathematically, what we do is we say, look, in an inhomogeneous slab, the amount of attenuation that's going to occur is the integral through the object of how mu is changing as a function of path through that object, right? So mu now is a function of position along my ray, and my eventual computation of how many X-rays get through look like this, where I have the number that hit the front side of the object, and then I'm going along my ray, and I'm going to integrate the linear attenuation coefficient as a function of position along that ray in order to add up how much attenuation is occurring, right? And this equation is absolutely essential for understanding how CT works. Because in plain film chest X-rays, you get one projection, and each ray you get a detected intensity, and that's the brightness of your picture, like that hand we put up. In CT, you would like to know the linear attenuation coefficient values all along your ray. You want a three-dimensional picture. And so that's what we're going to solve for in CT, is now that we know the number that got through on that ray, we also know that it was the sum across all these linear attenuation coefficients. So if we take enough of those measurements from different angles, we'll be able to invert the whole thing and pull out what this function is, right? So it turns out, as we saw in our chart here, attenuation is also proportional to the energy, right? So that basically you get much more attenuation at lower energies than you do at high energies. It takes 1.8 centimeters of muscle to reduce the photons by 50% if they're 30 keV photons, versus 150 keV photons, it takes 4.5 centimeters of muscle to reduce it by 50%. So there's an issue here, right? And that is, we know that coming out of our X-ray source, out of our tube, we have a whole spectrum of X-rays. And so how are we going to cope with that? If you wrote it down explicitly, you would say my intensity at my detector element is proportional to this integration over space along my ray, right? But I have to evaluate also mu as a function of energy over all of my energies, right? So I should think of it this way. Let's break up my energy spectrum into 100 bins. I'll make 100 pictures, right? And I'll have a value of SE for each one of those bins, right? And add all of that up, and that gives me my final image. Okay? And so this term here is kind of a pain in the neck, right? In terms of it's got an extra set of things we have to solve for that we may not have enough data to solve for. And so oftentimes what is done is, most of the time, is you just say, well, we'll call the beam an X-ray beam with an average energy. And we'll just put one energy in there. It'll be somewhere in the middle, right? And we'll solve it that way. So here are some actual values of mass attenuation coefficients, the mu values. You can look this up. Here's the website here for all of these tissues in folks at 20 keV and 100 keV, and these are the values. And you can see why a half value layer makes more sense to remember, because these numbers aren't that intuitive in terms of what it maps out to in space. But anyway, all the values are very well measured, very well known. Okay. And if we look at the linear attenuation coefficient, so this is the mu value, right, as a function of energy for different tissues, the functions look something like this. So at low energies, I get much higher attenuation. So those mu values are always higher, and then as I go to higher and higher energies, that reduces, right? So it would seem that, if you were to say, well, if I really wanted to, get the best contrast, the biggest fractional change between, let's say, fat, which is this curve, and muscle, and I had a choice of doing it at a specific energy, where would I do that? So it looks like it gets bigger as you go here, right? So you get much more contrast here. However, if we imaged at this keV, none of the photons would get out of the back of the patient, right? So you basically have to move this way in order to get a signal coming out of the back of the patient. And defining where along here you're going to work, there are many other issues that go into defining what the keV is that you're going to use. In the past decade, essentially CT used to always be done around here at 120 keV because X-ray tubes were built that way. That's what they put out. But then now that we have a whole new generation of tubes that can give you 80 keV beams, keV peak beams at really high MA, so like 1400 MA at 80 keV. So you still get stuff coming out of the back of the patient because you have enough going in the front side. But they are at a lower energy, and so it turns out the dose is much lower to the patient. And one of the things we don't do in this course is actually a detailed computation of dose, which we don't really have time to do it, unfortunately. And then contrast agents. This is Hypake, which is just a commercial contrast agent. It's not used them. Well, I think it's mostly swallowed. But it's a sort of organic molecule that has iodine in it, sort of 3 or 4 iodine atoms in the molecule. And so iodine is a great X-ray attenuator, and so you get really high values of the linear attenuation coefficient in these contrast agents. And then there's a K-edge, right, at 33 keV, which bumps the contrast up once you get to a high enough energy that you can eject that K electron from the inner shell. So here I can't eject that electron with a photon of this energy. As I go to higher and higher energy, finally I can knock that that electron out of the K shell. And so all of a sudden the attenuation value goes way up because I'm starting to get those interactions as well. So these are called K edges. And so when you swallow this stuff, this is what it looks like, right? You get really high attenuations through the contrast agent. And this is in a bowel. After you swallow it and you image the bowel, this is, what it looks like. There's our friend again, ready to swallow that milkshake. And as we saw last time, the arrow. This is the contrast this is omnipaque, which is another iodine-based contrast agent to improve the contrast of vessels. We saw that last lecture. And it's also done in neuro imaging, and this actually is in a fluoroscopy system where the patient is lying on a table. You can be doing some kind of intervention, and oftentimes say they have an aneurysm in one of the vessels in their brain that you have to go in and either clip off or put a coil in or do something like that. Then you can inject a contrast agent and watch it go up into the brain and image with super high resolution on an X-ray fluoroscopy system while you're doing that intervention. And that looks like that thing. There's a big red arrow. That doesn't happen with the system, because that was put there by a human. But this is obviously some kind of aneurysmal growth there. These are really dangerous. You don't want to leave that alone because it'll pop one day and bad things happen. Okay, the last thing, we got 1 minute. We'll talk about beam hardening. And this is also in the book. So here's the X-ray spectrum, relative number of X-rays as a function of energy. Right? We've clicked our tube to 100 keV peak, so that's the highest energy we can see. And this, if I look just at the tube, just outside the tube, I would see this spectrum, right? When I put a filter, right, between the tube and the patient, say a copper filter, then I get rid of all of these low energy, like down here, I get rid of this entire set of photons here by being absorbed by that filter. So they're not going to hit the patient. Remember, they wouldn't have done us any good anyway because none of them would have got through. And so this is the spectrum that is post-filter hitting the patient, right? This is the spectrum leaving the patient, right? And so basically all of these lower energy photons got observed. They're not going to help us make a picture. They're all in there, but we don't have any contrast from them. And this is the spectrum here. And so the mean energy, sort of the average energy of that spectrum, what happened to it? It started down here, and it shifted up to here. And this is called beam hardening. And so one of the issues with X-ray imaging, if we're going to take multiple views of an object, is as we go through on one path, the beam itself of X-rays along that line, as I move through that line, the average energy in that beam gets higher and higher and higher as I move along, right? So the X-rays that are hitting stuff towards the back of the patient are different than the X-rays that entered the front. The ones that entered the front had a lot more lower energy X-rays than the ones that are close to the back. That's called beam hardening. And we will stop there. And then next lecture, we're going to start looking at more mathematical descriptions of linear systems and things like that. Okay? So I'll hang around for questions if you have any questions.